$10 million. That's what it costs to deliver a single ton of water to the moon from Earth. But in permanently shadowed craters near the lunar poles, where temperatures plunge to minus 198 degrees Celsius and haven't seen sunlight for billions of years, spacecraft have detected an estimated 6 billion metric tons of water ice. One prominent lunar scientist referred to this as potentially the most valuable piece of real estate in the solar system. In this video, we'll explore how missions discovered this ice, what makes it so economically significant, and why multiple nations are racing to extract it before 2030. For decades, scientists believed the moon was completely dry. Early telescopic observations in the 1600s interpreted dark lunar patches as seas, but by the 1960s, Apollo astronauts confirmed the visible lunar surface contained virtually no water. Mission samples showed the regolith bone dry, with water content measured in parts per million at best. The prevailing model suggested that the moon's formation, created from debris after a Mars-sized object impacted early Earth, generated temperatures hot enough to vaporize all volatiles. Any hydrogen that might have existed would have escaped to space. This understanding dominated lunar science through the 1980s. The search for lunar water began systematically in January 1994, when NASA's Clementine mission entered lunar orbit. Clementine carried bistatic radar operating at S-band 2.273 GHz, transmitting right circular polarization at 6 watts. The spacecraft's primary task involved testing infrared sensors and optical systems developed for military applications, but mission planners included the moon's polar regions in the observation plan. Data suggested unusual radar returns from permanently shadowed areas near both poles. This prompted NASA to launch Lunar Prospector in January 1998, specifically to investigate these signals. Lunar Prospector carried a neutron spectrometer capable of detecting hydrogen to within 50 parts per million resolution, focusing on regions that never receive direct sunlight. These permanently shadowed craters exist because the moon's rotational axis tilts only 1.5 degrees from vertical, compared to Earth's 23.5-degree tilt, creating conditions where crater floors remain in perpetual darkness for billions of years. Lunar Prospector's neutron spectrometer, operated by detecting moderate-energy epithermal neutrons, created when high-energy galactic cosmic rays impact the lunar surface. These cosmic rays break apart regolith atoms and scatter subatomic particles. Neutrons ping-pong through the soil up to approximately 1 meter deep, colliding with other atoms. When neutrons collide with hydrogen atoms, which have nearly identical mass, they lose significantly more energy than when hitting heavier elements common in lunar rock like silicon, oxygen, or aluminum. By measuring the energy spectrum of neutrons escaping into space, the spectrometer could map hydrogen concentrations across the surface. The instrument maintained an 18.6-mile diameter field of view and orbited at approximately 63 miles altitude during its primary mission phase. However, the spectrometer couldn't distinguish between different hydrogen-bearing compounds. The detected hydrogen could indicate water ice, but might also represent hydroxyl radicals chemically bound to minerals or trapped hydrogen from the solar wind. Lunar Prospector detected enhanced hydrogen concentrations in permanently shadowed regions at both poles, with the North Pole showing stronger signatures than the South. The data indicated possible water ice deposits buried beneath as much as 40 centimeters of dry regolith. Initial estimates based on March 1998 measurements suggested approximately 300 million metric tons of water ice at each pole. The hydrogen signature appeared concentrated in specific crater floors rather than uniformly distributed across broad regions. mission controllers deliberately crashed the probe into Shoemaker Crater on July 31, 1999, hoping the impact would liberate detectable water vapor. Earth-based telescopes observed the debris cloud but detected no spectral signature characteristic of water, suggesting the ice existed as small, discrete pieces mixed throughout the regolith, rather than as a thick, pure layer. Subsequent missions refined these findings. On October 9, 2009, NASA's LCROSS mission deliberately impacted Cabeus crater near the South Pole. Analysis of the ejecta plume indicated water content of approximately 5.6% by weight in the impact area, including nearly pure ice crystals in some locations. India's Chandrayaan-1 mission, carrying NASA's Moon Mineralogy Mapper, revealed hydroxyl signatures across much of the sunlit lunar surface in 2009, not just in shadowed craters. The Mini-SAR radar experiment on Chandrayaan-1 indicated possible large deposits totaling an estimated 600 million metric tons in northern lunar craters. More recently, NASA's Lunar Reconnaissance Orbiter mapping in 2024 showed ice deposits extending beyond the South Pole to at least 77 degrees south latitude, distributed more widely than earlier estimates suggested. Scientists propose several mechanisms for how water ice accumulated in these permanently shadowed regions. One interpretation suggests comets and water-bearing asteroids bombarded the lunar surface over billions of years. Water molecules from these impacts vaporized on contact with the sunlit surface, but migrated as gas until reaching cold traps in shadowed craters, where temperatures below 75 Kelvin allow ice to remain stable indefinitely. Another model proposes that hydrogen ions from the solar wind continuously strike the lunar surface, react with oxygen in minerals to form hydroxyl and water molecules, which then migrate to cold traps. A third possibility considers that some water originated from the moon's interior, released through volcanic activity billions of years ago, and subsequently trapped in polar shadows. The distribution pattern observed by Lunar Reconnaissance Orbiter suggests ice concentrations are greatest near the coldest locations below 75 Kelvin and near the base of poleward-facing slopes within permanently shadowed regions. However, the data indicates this ice likely exists as small pieces less than 10 centimeters in size, distributed throughout the regolith, or as thin coatings on soil grains, rather than thick, pure ice sheets. Some researchers note that alternative explanations for the hydrogen signatures remain possible, including concentrations of hydrogen molecules from the solar wind, rather than water ice. Current remote sensing data cannot definitively determine the precise form, depth, or concentration of lunar water ice deposits. The neutron spectrometer and radar observations provide indirect measurements that detect hydrogen or altered surface properties, not water ice directly. The instruments cannot accurately determine whether deposits exist as buried layers under dry regolith or as ice intimately mixed with soil particles. Estimates of total ice mass carry substantial uncertainty. The figure of 6 billion metric tons represents a model-based calculation that could vary considerably depending on actual deposit characteristics. No mission has yet physically sampled ice from a permanently shadowed crater to confirm its composition, isotopic signature, or geotechnical properties. The ice depth, whether deposits extend 1 meter down or several meters, remains unconfirmed. These uncertainties matter critically for future extraction operations, which require knowing whether to mine surface regolith or drill deeper, and whether the ice concentration justifies processing costs. The economic significance becomes clear when compared to terrestrial mining operations. On Earth, water costs virtually nothing to obtain. Municipal water typically costs less than $1 per ton. But launching water from Earth to the Moon costs between $20,000 and $50,000 per kilogram, depending on the launch system. That translates to $10 million per ton delivered to lunar orbit. A 10-ton Mars mission payload requiring propellant would cost $200 to $500 million just for fuel launched from Earth. By comparison, economic studies suggest lunar water could be extracted and processed on the Moon for approximately $0.5 million per ton. Even if extraction costs run several times higher than estimates, the margin remains compelling. One analysis proposed that a modest operation producing 245 tons annually would generate $2.4 billion in revenue per year, based on current Earth-to-Moon transportation costs. Water represents the feedstock for rocket propellant. Electrolysis splits water molecules into hydrogen and oxygen, creating liquid oxygen and liquid hydrogen propellant that comprises 89% oxygen by weight. For comparison, Earth's deep seabed mining targets polymetallic nodules containing cobalt and nickel in international waters. Like lunar ice, seabed resources exist in harsh, largely unexplored environments requiring specialized autonomous equipment. Both face similar governance challenges regarding access rights and environmental protection in areas beyond national jurisdiction. Lunar water ice represents the foundation for what space industry analysts describe as a cislunar economy, sustained human and robotic activity in the space between Earth and the Moon. Every kilogram of propellant produced on the Moon, rather than launched from Earth, reduces mission costs and enables more ambitious exploration. Mars missions particularly benefit, as spacecraft could refuel in lunar orbit before the interplanetary journey, dramatically reducing the fuel mass that must be lifted out of Earth's gravity well. Beyond propellant, water provides radiation shielding for habitats, drinking water for astronauts, and oxygen for breathing. Processing 2,450 metric tons of lunar water annually could support propellant demand for both government and commercial missions, creating an industry that makes deep space access economically sustainable rather than dependent on constant Earth resupply. NASA's Artemis program aims to establish sustained lunar presence beginning in the late 2020s, with landing sites selected near the South Pole specifically for water ice access. The Viper rover mission, planned to explore permanently shadowed regions, will carry instruments to sample various soil environments and map water resources. Intuitive Machines' IM-2 mission, launched in February 2025, carries instruments to Mons Mouton at 85 degrees south latitude to measure temperatures and demonstrate ice detection methods. China's International Lunar Research Station plans include automated ice extraction capabilities in the 2030s. The 6 billion metric tons of lunar water ice represents more than frozen molecules in shadowed craters. It's the difference between space exploration as expensive government expeditions and space development as economically sustainable enterprise. Whether nations cooperate or compete for access to the richest deposits, whether extraction technologies work as predicted in the lunar environment, whether governance frameworks emerge to manage these resources, these questions will shape the next phase of human expansion beyond Earth. If you found this exploration of lunar water ice valuable, consider subscribing to Orbital Atlas for more evidence-based space content. What aspects of lunar resource utilization interest you most? Share your thoughts in the comments below. All visuals in this video are illustrative and created for educational purposes, based on proposed engineering concepts discussed in scientific research and official space agency publications.